So thank you for joining me, everyone, over here. So today I'm going to talk about recommender systems. So first, a little bit about me. So my name is Divya Sardana. I am doing my PhD in computer science in the area of machine learning from University of Cincinnati back at Ohio. And my dissertation area specifically is in graph mining. So what I did in my dissertation is I built a new graph clustering algorithm, and then I applied it to different real-world data sets, mostly protein interaction networks and then some social network. And recently I applied it to a geotemporal network of all the crimes taking place in San Francisco. I did some clustering and more analysis over that. So today, I'm going to talk about recommender systems using Python. Okay, so let's get started. So here is a brief outline of my talk today. So first, I'll talk about why do we need recommender systems. And then we'll discuss some examples of recommender systems. Then we'll move on to building some real-world recommender systems. So we'll cover three types of categories of recommender systems today: popularity-based recommender system, then classification-based, and collaborating filtering-based. And then finally, we'll discuss an evaluation measure to evaluate different types of recommender systems. Okay, so let's get started. So why do we need recommender systems? So let's begin by thinking about the traditional view of how the shopping used to take place earlier. So this is this is a traditional bookstore wherein we have a limited set of books which are limited by what can fit in the brick and mortar store, and sometimes the popular books would be listed over here in the center. So it was easy for the shoppers who used to just go to the store and pick from whatever is lying there inside the store and buy whatever they liked. But now, coming back to what's going on today is that we have these huge set of products online, and there could be let's take the example of music, for example. So somebody could be selling some music online, which is very old music from 50s, which some traditional tribal African music. So there is now a set of very niche products which fill the market today. So this leads to a phenomenon, something called as the long tail phenomenon, where these orange set of products represents the popular products which we can find both in retail stores as well as online. And then there is a huge set of products which we find only in online stores. So we need some system which tells us that these will be relevant items for you to look at as compared to just bombarding the users with so many choices. So what a recommender system does is, the goal of a recommender system is to identify products which are most relevant to the user. For example, top 10 promotions, top 10 news articles. Okay. So some examples. So what are some examples of real-world recommender systems? Anybody? In the real world today? Amazon, yes. How about movies? Netflix, yes. So let's see, movie or TV show recommendations like from Netflix, then product recommendations by Amazon, then friend recommendations in Facebook, right? And then job recommendations. LinkedIn sends you many emails almost every now and then that these jobs match you perfectly. And then, okay, so before we move on to building recommender systems, let's first gain a naive understanding of what a recommender system means. So let's think about, in the real world, when I'm going to shop something, how do I go about this shopping process? So let's say today I want to go eat something new. So my friend here tells me that, hey, I ate this new dish at some newly opened Thai restaurant. So you must go and try that dish out. And then I think, okay, my friend is recommending this to me, and I know that my taste is similar to my friend, and I should go to that Thai restaurant and try that dish out. And then sometimes my sister would tell me that I bought this dress from this store, and you must go buy this dress. It's such a nice dress. And I will think, okay, I will take her recommendation. And then sometimes my professor will tell me that you must read this book. It's a very nice book about machine learning. And I might take his recommendation and read that book. So you see, what we have in our system is a set of users on the left-hand side, and then a set of items on the right-hand side. So the users, they might be related to each other, and then the items might be related to each other. For example, different books on machine learning are related to each other. Dishes related to a cuisine might be related to each other. And then there is a mapping between users and matching items. And then a recommender system, it exploits this mapping between users and the matching items in order to make recommendations. So it is just as similar as we will do recommendations in the real world. It's just that now we are doing it in a clever way using a machine learning algorithm called recommender system. Okay, so a quiz now. So let's go back to the real world examples which we talked about before. So what are the users and matching items in the following cases? LinkedIn. So what are my users in LinkedIn? The members of LinkedIn. And what are my items in LinkedIn? Jobs. Yes. So what about Facebook? What are my users here? Members. And what are my items here? Members. Again, members. Yes. And what about Amazon? The users are again members, and items are items, yeah, products, the books and whatever Amazon is selling. Right. And then how about Netflix? Users are members, and then items are movies. Yes. So this was simple. Okay. So before we move on now, I want to talk about this success story of recommender systems, that how it can have a huge impact in the market. So, for example, so these are two books about mountaineering adventures. So this book on the left-hand side called Touching the Void came out in 1988 by the author Joey Simpson, and it became a modest success at that time, and then they forgot about this book later on. And then another book called Into Thin Layer, it came out by John Crocker in the year 1996, and it became a huge sensation. And then what happened was that Amazon, it picked up that people who were buying this book about mountaineering adventure called Into Thin Air, they were also buying another book called Touching the Void. And then suddenly what happened almost a decade later is the other book, Touching the Void, instantly became famous a decade later. So you see, the recommender systems, if used properly, they can have a huge impact in the market. Okay. So now we can move on to building a recommender system. So we'll start with the very simplest solution to build a recommender system. So it's called a popularity-based recommender system. So let's first consider this example about popularity-based recommender system that we all see when we read news daily. So you see on Google News, when we read news, we see it lists, these are my most popular news. And then when you go to some clothing stores, say Kohl's, it might list, these are my popular products. So how do they calculate what are the popular products? A very simplest approach would be to calculate popular products simply by a count of purchases. So all those products, for example, in this dressing store, store, the popular products could be calculated based upon products which are being bought the most. Does that make sense? Right? So, and similarly in news, the most popular news would be the news articles which a lot of people are reading during that day. So essentially, my recommendations here are a ranked list of items by their purchase count, right? So, okay, so now a quiz. So which one of the following is true for a popularity-based recommender? Can it generate personalized recommendations? Yes, no, correct. So, for example, if I want recommend what are the popular news for me versus you, popular news for the day would be the same, right? Okay. So the correct answer is no. Okay. Second, can it use context? For example, time of the day. I mean, so we could say that these are my most popular items during the morning versus the evening. For example, some shoppers, they purchase these popular items during the evening, Friday evenings. So we could say that it could use context in some way. Can it use user features? So user features would be what is the age of the user, gender of the user. Can it use user features? So I would say the answer is it can use user features, but it won't be very meaningful. The only, for example, what are the most popular items amongst teenagers versus 30-year-olds? So but it won't be. It is just that the meaning of that it is possible to do, but it may not be very intuitive. And then can use item features. So item features would be like what is the size of my item, what is the color of my item, cost of my item. So again, theoretically, it is possible to do that. That what are the most popular Nike clothings, but it may not be very meaningful to suggest those items on a website. Can it use purchase history? So yeah, so we are using purchase history, like the most purchased items in the past. It uses purchase history of the users. And how about scalability? Is it scalable? Yes, so simply we are just sorting all the items by their purchase count. So yeah, so we just need to do sorting. So it is scalable, yes. Okay. So let's move on to our little more complicated solution now. So a second way to build a recommender system could be to use a classification model. So you know about simple linear classifications like logistic regression or naive Bayesian classifier. So how about we use such type of classifiers to build a recommender system, which so for example, we have on the left-hand side, the input to the classifier could be my user features, such as age of the user, gender, then product features like cost or quality of the product, and then purchase history. And we could have these as my input features in my classifier, and then the classifier could give an output, just a binary output, like a new user which comes in, will he like the item or not like the item? So, for example, the classifier could help us separate all teenagers who have some fashion, very different fashion style as compared to all 30-year-old people who go to office. So such type of classification method can help us build these categories, which we could exploit to build mappings between users and items, and hence build recommender systems. But what is a limitation of this approach? Is it how easy or difficult is it to collect such data? Oops. So in a real world scenario, it is difficult to collect such information. Okay, so a quiz now. We'll keep going on. So which of the following? So which of the following is true for a classification-based recommender system? Can it generate personalized recommendations? Yes, so it is using user features, item features. So yes, it can generate personalized recommendations. Can it use context? For example, time of the day. Yeah, so time of the day could be one feature in my classification input classification model, right? Okay. All right, so can it use user features? Yes, so it can. And then how about item features? Yes, in the classification model. Can it use purchase history? Yes, it can. And then how about scalability? It might not be very scalable because when my features and when a lot of data comes in, then it might be difficult to build a classification model and that to keep on updating it when in a very online manner. Okay. So the next set of recommender systems would be my nearest neighbor collaborative filtering. So in these collaborative filtering types of recommender systems, the recommendations are based upon the nearest neighbors. So nearest neighbor approach is used to find out either similar users or similar products. So this type of let's try to first gain an intuition of these type of methods. Let's look at this figure. So this is about some people and what fruits they buy from some store. So this problem of collaborative filtering can be looked at in two ways. One way would be to look at the similarity between users, and the other way would be to look at the similarity between the items. So let's look at the first way first. So we can say in this left side figure that the first girl and the last boy, they are similar in some terms because they have a similar taste in what fruits they like. So for example, both of them have purchased strawberries and watermelon. So we can say that they have a similar taste. So now so we can use this similarity information in order to recommend to this boy whatever the girl was eating. And so the grapes, the boy didn't try grapes yet, so we can recommend grapes to the boy, right? So exploiting similarity between the users. And then let's move on to the figure on the right-hand side. We will say that grapes are similar in some sense to watermelon because many people have been buying them together. So of course, there may not be like a real similarity between the fruits, but they are similar in terms of recommender systems because many people have been buying them together. So the two girls above have been buying these two fruits together. So therefore, when the boy here, he purchases watermelon, we will recommend him the next nearest neighbor to watermelon, which in this case is grapes. So what exactly in this approach we would say? So in the left-hand side approach or the user-based filtering, we would say something like user X is similar to user Y because both purchased items A, B, and C. But about item-based collaborative filtering, what we would say is that items A and B now were purchased both by users X and Y, so they are similar. Right? So you see the difference in the two ways of looking at the same problem, right? So in this talk, I'm going to focus more on item-based collaborative filtering. But in similar ways, we can map the same problem to user-based collaborative filtering as well. Okay, so let's go into more detail of item-based collaborative filtering. And let's talk about here an example of movies. So on my left-hand side, we have some sample users, Ted, Carol, and Bob, and the movies they have been watching, movies A, B, and C. And let's call this as our purchase history matrix in this case. So in this method, what we do, given a history matrix, is that, first of all, we build a co-occurrence matrix. What do we mean by a co-occurrence matrix? Is that we take all the items here, or in this case, all the unique items, in this case, they are the movies, and we create a matrix between all possible combinations of items. And what are the values of this matrix? So the value is that how many users have seen both movie A and movie B. So So in this case, for movie A and B, we can see here that only Ted has watched both movie A and B. Therefore, we will have a 1 here. And then how many users have watched both movies A and C? We can say Ted has watched both A and C, then Carol also has watched both A and C. So therefore, we'll have in the co-occurrence matrix 2 here. So now the question here is to generate recommendations for Bob. So what we do here when we need to generate recommendations is that we see what all movies Bob has already watched. In this case, Bob has watched movie A. Then what we will do is we will go to the co-occurrence matrix now, and we will see the row for this movie A. And then we can sort this row in descending order, and then we can give out the recommendations for Bob here. So what is the intuition behind sorting them in descending order is that it will give us an intuition that what most people have been viewing, we want to recommend them first, right? Okay, so in this case, Bob's recommendations would be, the top recommendation for Bob would be C, and then the second best recommendation for Bob would be B, right? Is that clear? Okay. So, so now let's look at some effect of very popular movies. So let's take an example of a very popular movie, let's say Titanic, which let's say all our users, almost everyone has seen this movie. So, in the co-occurrence matrix, when we get this movie in the co-occurrence matrix, we can see that this value may be very high for almost all the users, right? Because every person has watched that movie, so the co-occurrence of this movie with each other movie will be very high. So what now if we want to recommend movies for Bob, we will look at the row for the movie which Bob has already seen, in this case movie A. So what would be the movie recommended to Bob in this case? Titanic, right? But so this means that this recommender system would almost behave like a popularity-based recommender system. So whatever my popular items are, they would be recommended. So we don't want this. It would not be very interesting. So how do we deal with the effect of such popular items? How do we do that? So most frequently, what we do to deal with this problem is normalization. So we normalize our co-occurrence matrix by popularity. So generally, there are many methods of normalizing. The very basic and naive method of normalizing is this Jaccard similarity measure, wherein we will divide all the cells of this co-occurrence matrix by the number of users which have watched either of movie A or movie C. So remember, our numerator here was the number of users who have watched both. It is the intersection on the numerator, both A and B. It was 1 in this case. In the denominator, now we have a union of users who have watched movie A or movie B. So that in this case is 3, right? So it will be divided by 3. In this case, would be divided by 2. And for the Titanic case, it would be divided by 100,002. It would be a very small number now. So now what would be the topmost recommended item for Bob here? Yes, so it would be C. So that is what we wanted. So you see, normalization has helped us deal with the effect of very popular items. Okay. So let's consider another case now in which Bob has watched more than one movie now. So earlier Bob had only watched movie A. Now Bob has watched more than one movie. So in this case, how do we recommend more items to Bob? So remember earlier we were looking at the only one row in the co-occurrence matrix for movie A. Now we have Bob has watched another movie called movie D. So what we will do is that we will look at not only row A in this movie and another row D. Suppose there was another row here for movie D. We will take out both the rows A and D from this matrix, co-occurrence matrix, and let's say we list them out here. And remember, it's a normalized matrix this time, normalized co-occurrence matrix. So then what we do is that we simply take a weighted sum of these columns and list them out here. So in case Bob has watched so many movies, we will take all those rows out, and then we will simply take a normalized sum of all those rows in order to get our final recommendations. So in this case, the topmost recommended item for Bob would be movie C, right? Okay. So now a quiz. So given a user item ratings matrix of size 480,000 cross 17,000, approximately 17,000, which model will you apply given the matrix is very sparse? Popularity-based recommender system, how about that? So I would say maybe we could apply that, but it wouldn't make any sense here, because we could simply take it could simply tell what are the most highly rated movies, but it won't help us much here. And one thing we need to keep in our mind is that this matrix is very sparse as well. Okay. Then,
because it's sparse, you're weighting to the top picks, right?
yes, the top high.
If it weren't sparse, then that would possibly be a very good choice, right?
It would be a good choice, but it won't be personalized, I would say. So depending upon our problem, these days we want personalization is a big thing. So it may not be very useful.
Yeah, but sparse being the key word on the popularity base that has a big weight, right?
Say again?
Sparse is the key word that you're looking for when you're trying to decide.
Mm-hmm. Yes. Okay, so how about a classification model? No, so it again may not be the best one to do. Okay, how about an item similarity based recommender system? Remember, we just talked about it, in which the item similarity based recommender system, wherein we need to build a co-occurrence matrix. So what would be the size of my co-occurrence matrix in this case? 17,000 cross 17,000. And moreover, in the previous slides when we were talking, the co-occurrence matrix simply was the history matrix simply listed whether the user has watched a movie or not. It was a binary matrix over here. This history matrix on the left is a binary matrix. Now we are given ratings. So if we are using item-based similarity model, we are not making any use of these ratings, right? And similarly, user-based similarity, user similarity-based recommender system, again, may not be the best choice in a similar way. So all of the above is definitely out of the question, and seems like the answer is none of the above if we don't count popularity-based recommender systems. So you must be thinking whatever we have done so far, it may not be very applicable in the real-world cases, wherein we might be having many sparse matrices out there. So why did I choose this matrix, 480,000 cross 17,000? Anybody knows about this matrix? Yeah, so this is $1 million matrix. It's worth $1 million. It was released as a part of Netflix competition somewhere back in, I think, 2006. It was released, and the goal was to come up with a new algorithm for recommender systems which would improve the accuracy of over the existing Netflix algorithm by more than 10%. And this matrix over here has about 100 million ratings. You think that's a lot of ratings? No, seems like it is not a lot of ratings, because it means that so the total possible ratings here is 480,000 multiplied by 17,000, which is 8.5 billion ratings, and out of that we have only 100 million non-zero values, which is just 1% of the whole matrix. So it is indeed a very sparse matrix. So what do we do in such cases when we have sparse matrices? So what helps in this case is our third solution, yes, actually here, which is a model-based collaborative filtering method, or a matrix factorization based methods. So so another problem which would occur, which we missed in this slide, is that it would be the matrix is sparse. That is one thing. Another thing would be, in order to store as an item cross, in order to store, in case of item similarity based method, storing 17,000 cross 17,000 matrix each time when we are using the model, it may be very inefficient. So what model-based collaborative filtering methods they do is that they take the input user ratings matrix and then they build a model in a low-ranked dimensional space. And they generally use some existing matrix factorization based methods. So what do we mean here by a low rank dimensional space is that these matrix factorization methods, they identify a hidden dimension, or in a way we can say that they identify latent features from the input user items ratings matrix to represent user and items as vectors in n-dimensional space. Let's try to understand this using this example over here. So what do we mean by user vectors and item vectors? So intuitively, what our matrix factorization here is doing is that, so we have this input user ratings matrix. It is very sparse, right? And it has, but it still has some non-zero entries. So it will take that user ratings matrix and convert it into a user matrix of vectors and a items matrix of vectors. What are my vectors here? So my vectors here, user vector and item vector, could look something like this. So in case of movies, it is telling me that how much that user likes these serious movies. So what is the genre of my movie? It would be, so for example, my different genre could be how comedy, horror, or in this case, serious, escapist, geared towards males or females. So if you know about information retrieval based classes wherein documents are represented by vectors, you could think of it something in a similar way, wherein we are representing users as vectors, wherein each value in our vector is telling us that how much the user likes how much the user can be represented for each genre. And then when we represent these vectors in this low dimensional latent space over the left, which is in this case is a two-dimensional space, we can see that we could represent all the users in this space, and then similarly all the items also could be, in this case the movies, could be represented here as well. So what happens now when a new user comes in? So new user comes in, and we have this input matrix of users and items, and then we will, and now our matrix factorization has given us user vectors and item vectors, right? So we will use that matrix factorization to get a representation of this user as a user vector. And then this user can be represented in the same latent dimensional space. And when we represent this user like that, now we know in this space that what all are my movies which are located near me in this latent dimensional space. And then we can exploit this information to recommend movies which are close to the user in this hidden dimensional space, right? Okay. And just going into a little detail about matrix factorization. So most common method of doing matrix factorization here that is very used as singular value decomposition. So let's think of matrix factorization in a way that we all know about integer factorization, right? Maybe we read about it in our elementary mathematics that, for example, how about integer 12? What are the prime factors of 12? Yeah, 3, 2, and 2. So you see, if we factorize an integer, the 12, we get prime factors to 3, 2, and 2. What do these prime factors tell us? They tell us that any multiple of 12, say 144, will not be divisible by, say, 5, because 5 is not a prime factor of 12. And no matter whether we represent 12 in binary form or octal form, hexadecimal form, 12 will always have these prime factors, right? So matrix factorization, it tells us about some universal properties of that mathematical object, irrespective of how we represent that mathematical object. And then that factorization helps us to gain some intuitive ideas about that mathematical object. Now we transfer that our knowledge about integers to matrices over here. So in the similar way, when we factorize a matrix using some matrix factorization method, then it tells us some interesting information about in the user space. So from the previous example, it was telling us some interesting information about the users. For example, this user likes comedy movies very much, and he doesn't like horror movies a lot. And we are quantifying it by assigning some values to how much he likes comedy movies, how much he or she likes horror movies. So this matrix factorization is, in a sense, what it is doing is that it is extracting this most interesting information about users and items, and then this interesting information, it is quantifying it, and this quantification is in some way helping us to predict the ratings for new users. Right? So remember, this matrix was a very sparse matrix. This sparse matrix will be used to by the matrix factorization method to get this user movies, matrices of user vectors and movie vectors. And then these matrices will then be used to fill all the zero cells in the matrix in order to make recommendations. Right. So yeah, this is what I just talked about, that mathematically we can represent the SVD by this, mathematical formula. And then, so the winning entry of the Netflix prize, what it used is a number of SVD models, including some SVD ++ or restricted Boltzmann machines. And they achieved, I think, slightly more than 10% accuracy over the Netflix existing information. And then I have listed a paper here where it talks about, if you want to read more about the Netflix prize and how the matrix factorization method was used here, I would recommend you to read this paper. Okay. So now some performance metrics for recommender systems. So the most commonly used performance metric here are precision and recall. So let's understand this by an example. So let's say I only like Will Smith movies, and I don't like any other movies. And but still, what I was recommended was, I was made some recommendations for some Will Smith movies and some Johnny Depp movies as well. So what are my relevant items? Relevant items meaning all those I like. So the relevant items will be all these items, all the Will Smith movies, and the recommendations will be a combination of some of the Will Smith movies and some Johnny Depp movies, right? So so these here in this cell represent relevant items that are also recommended, and this cell represents irrelevant items or the Johnny Depp movies that are recommended, which I don't like. And then this cell recommends the Will Smith movies, which my recommendation algorithm didn't recommend me. So how is precision calculated is, it is calculated as the number of products which are relevant and recommended in this cell, divided by all the number of items that are recommended. So in this example, all the Will Smith movies which are recommended, divided by all the Will Smith and Johnny Depp movies that were recommended to me. And then recall, how is it calculated? So precision is in a way a measure of exactness. How exact are my predicted recommendations? And then recall here would be calculated as number of products which are relevant and recommended in this cell, divided by the total number of relevant items. So here in this example, all the Will Smith movies which were recommended, and then all the Will Smith movies which I actually like. So intuitively, what recall is doing is, it is a measure of completeness, that whatever movies I liked has have every one, each one of that movie, has it been recommended or not? So these are two important measures of evaluation. And then what we mostly generally do in order to compare recommender systems is that we build precision recall curves. So what we normally what is done is that we recommendation algorithms, they will recommend top n items. So this algorithm, this curve, what is it? It is representing is that, so we will calculate precision recall for, say, top 1 recommendations for all the users. We'll plot a point here. Then top 2 recommendations we will take for all our users. Then we will calculate average precision, average recall for all the users. For top 2 recommendations, we will plot a point here. So what this is representing is that as we go from top k recommendations to top k plus 1 recommendations, how is the quality of recommendation engine changing? So why is this sawtooth pattern? So think about it, that if we go from top k recommendations to top k plus 1 recommendations, two things can happen. The k plus 1th recommended item would be either whether I will like or not. So for example, in our previous example, if the k plus 1th item is a Will Smith movie, which I like, then both precision and recall will go up. And this represents this increase in this sawtooth pattern. And what if the recommendation in this case was a Johnny Depp movie? So precision would fall by 1, like this, but recall would remain the same because all the relevant items that have been recommended, the Will Smith movies, are still the same. So it will have, no matter what our recommendation system is, that we will get these, either we will go high like a spike where both recall and precision increase, or we fall down wherein recall remains the same or precision drops by 1. So these patterns will be the same in this curve. Okay. So performance. So there are some other performance metrics also, which such as mean absolute error, accuracy, and ROC curve. And I would recommend you to read this paper I have listed. It has a very good survey of evaluation metrics for recommendation tasks. And I also have a following notebook wherein we will be using precision and recall to evaluate different types of recommender systems. Okay, so this is my last quiz here. So comparison. So which recommender movie can handle brand new items? So for example, a newly released movie. So this movie, I think this Little Men movie was released, I think, just last Friday. So what do you think that which recommendation system would be the one which would pick that movie up and display recommendations? So this last column. So how about a popularity-based recommendation system? Will it be able to recommend My Little Men movie? No, right? Because this movie just doesn't have any viewing history so far. So how can it become popular so soon? I mean, it may be a very popular movie on the first day many people went, but as compared to many other movies which have been released since a very long time, they may be having such a huge view count, but this movie was just released. It is not in our system yet. So maybe popularity-based recommender system will not be able to handle this newly released movie. How about a classification-based system? Well, it will not be able to use purchase history, but it could use some features of the movie. For example, what is the cast in this movie? What are my actors in this movie? What type of movie is this? Is this a comedy movie, horror movie? And then based upon that, we could feed that in our classification model as features, and then we could get similar movies based upon just these features and not considering the purchase history at all. And still, yes, so this classification model-based method could help us, right? It makes sense, right? So how about a nearest neighbor-based classification system? Let's say item similarity-based classification system, wherein we were building a co-occurrence matrix of all items based upon co-purchase history. So do you think this movie will have any co-purchase history? Not really, right? Because it is so much of a new released movie, and there will be many few users who will have watched. So it will not be very fruitful to use an nearest neighbor based collaborating filtering algorithm for this movie. How about a matrix factorization based movie, based recommender system? So again, since it's a new movie, not many people would have rated it, right? So it may not be, again, a good idea to just simply use a matrix factorization method. So it seems like this problem has a name. It is called a cold start problem. So now in the real world, how it is handled is that, say, our model is using a matrix factorization based method to build a recommender system which is being used on a day-to-day basis, and then when new products come in, then we handle them using a classification-based method. So these models are called as hybrid-based recommender systems, wherein we are taking more than one approach and we are combining them. We might use one in some circumstances, another in some other circumstances, and then use both of them to give our final results. Okay. Yeah, so we are ready to go to our notebook, wherein we will recommend some songs. So this data set that we will be using is a million songs data set. So this is my link to the notebook here. So you can either download or clone this directory. So for cloning, there will be a link to the right side of my GitHub. You can copy this link and just use, if you have Git, you use git clone and then this name of the directory. Or you can simply download it and unzip it. So in Python, I built some of my own classes for building a popularity-based recommender system and an item-based, similarity-based recommender system. And we will be using that to recommend songs from the million songs data set. And then we will be also doing seeing a small demo of matrix factorization based method on a very small dummy matrix, so as to gain more understanding of how the latent semantic space is working. And then there is also in Python an existing package called crab. Don't know if how many of you know about it. It also does the job of doing recommendations for. It's a package for doing recommendations in Python if you want to check that out. Yeah. Okay, everybody has this link. Shall I move away from it? Okay. So I already have it on my system. Okay. Yeah, so this is the million songs data set source, what I was talking about. So we will be only working on a subset of this data set. So because it takes a long time for the code to run on the whole data set. And okay, let's move on. So what this first cell is doing is, let's import all the methods, all the libraries. Okay. So now we will load some music data. So this step might take a while on your system. So I didn't make a local copy of this data set because I got this. The original million songs data set is an open source data set by Columbia University. But this data set was a subset available at this site by Turi or Dato, and I wasn't sure I could keep that as a local copy. So it might take time for you to get this step done. But meanwhile, I will just go ahead. So let's explore this song data. How does it look like? So this data here has about songs, so we have user ID, song ID, listen count, and title, release, artist name, and year. So it is, in a way, what we need from this data set are these triplets: user, song, and then listen count. So what is my user, what is the song the user has listened to, and how many number of times the user has listened that song. Okay, so let's see what is the, shall I move forward? Is the data set loaded for you? Yeah, it might take some time. Especially we are on Wi-Fi here, and everybody is trying to download from the same link. But it should not be more than 3-4 minutes, I think. So initial steps are anyways just data exploration. So it's okay if it is taking a while. You can follow me over here. Okay. So let's see what is the length of this data frame. It's 2 million. And we'll create a subset of this data set so that we can run it all here at one go. So I just changed this 100,000 to 10,000 here because I think 100,000 will also take a long time here given the. So at this step, create the subset of the data set. Just change this to 10,000. And then what I'm also doing here is that I'm creating a new column in our data frame, which combines title and the artist name, so as to make our recommendations so that we can view them a little more meaningful way. Okay, so what are my most popular songs here based upon their listen count? Okay. So here I have simply, what I've done is just sorted the songs based upon how many, the listen count, how many users have listened to songs, and then calculated a percentage ranked list of all the songs. Okay? So let's count the number of users, unique users in the data set. So we have 365 unique users in the data set, right? Okay, so a quiz for you. So how about we now count the unique number of songs in the data set? How will we do that? So we can, a hint is that follow how we calculated the unique number of users here. We can take help from this code over here. And instead of user ID, we just can simply type here song. And this will give us the unique songs in the data set. Now we can check, let's call it songs. Okay. Yeah. So we see that there are 365 users and about 5,000 songs. So what does this tell us? This tells us that each user may be listening to more than one song, right? Because we have this number of songs is more than the number of users, right? So what does this suggest? That it is possible to find out similarity between users based upon how many similar songs they are listening to, right? Because it could be possible, right? At least we know that it is possible now, right? Okay, now how to do that? Let's figure that out now. Okay, so what we will do now is we will then split our training set into training and our data into training set and test set, keeping an 80-20 ratio. So how are we doing on the data download? Has everybody got the data? Not yet? Okay, when you get that data, I'll repeat that make the subset of the data set over here in this cell to 10,000 instead of 100,000 so that it will run smoothly for everybody. Right. Okay. So now we will create a popularity-based recommender system for users. So we will create an instance of the popularity recommender class. Oops. And then we will use the popularity model to make some predictions. Okay. So based upon my remember we had also listed the most popular songs in the beginning, and here again we have calculated a popularity for this user, which is users of 5. This method is calculating recommendations for this user. Okay, just to get an idea of how it is working. So this is a quiz for you to calculate recommendations for another user now, and to compare how do these recommendations compare with my earlier recommendations. You want to try it out? So what we can do is we can simply use our previous code to recommend. So earlier we were recommended for users of 5, and now I will do the recommendations for user ID, a different user ID, user of 7. So how do my recommendations compare with the earlier recommendations? So it is Seher Kosmish by Harmonica and Undo by Bjork. These are my top 2 recommendations for users of 5. What are my top 2 recommendations for users of 7? Is the same. So what does it tell us about a popularity-based recommender system? It is not personalized, right? So, okay. But it is very simple to calculate, right? That is the advantage. Just rank list based upon the listen count, and that's it. It's easy. Okay. So now let's build a song recommender with some personalization. So what we will do here is we will create an instance of this class over here. So far, are we going good here? Any question? A link for GitHub? Okay. Yeah, this is the GitHub link. Yeah.
I think it's on the website.
Yeah, I'll open it here. Yeah, so this is the link. Can you see this now? Okay. So everybody has a link now? Okay, I'll go a little slow now, that's fine. Shall I move over to the notebook now? Okay. I'll quickly repeat what I did so far, so as to, for those who are still catching up. So the first cell, we will import all the libraries. This includes the libraries for recommenders as well as evaluation. So the last two libraries, these are Python files which I wrote, and you can read more about them from the GitHub page. They include classes for different recommender systems, as well as the evaluation class contains code for precision recall calculation. And then this is a subset of the million songs data set, which we can download it. What this cell is doing is it is taking this data from the Story website. And so the first file here, the triplets file, what it contains is the triplets of user, song, and listen count. And the second file over here, songs metadata, what it is doing is it contains some information about the song, like artist name, title, and release, these different kinds of metadata information about the songs. And so what I did is I used pandas to read table, and then read this triplets file as a data frame. And then I read the song metadata as a data frame again. And finally, what I did is I merged these two data frames in pandas to create one single data frame, which contains not only our triplets, but also the metadata about the songs which we have in the triplets, right? And then we look at the head of the data just to see what is a snapshot of how the data looks like. We see that we have so far we are good till here? At the back? Okay, great. So we have user ID, song ID, listen count, title, release, artist name, and then year information. Okay? And then the length of this data frame is about 2 million. This means we have 2 million triplets here of user ID, song ID, and listen count. So what we are doing here, so in your notebooks, in this step, it would be a number here as 100,000, wherein we are taking a subset of this data so that it runs quickly over here. So I would suggest you to change it to 10,000 over here so that our code will run smoothly here. Right? Are we fine till this step? Right? So when we run this step, then our subset would be created. And then in this last line here, what I'm doing is I'm creating a more intuitive, so I'm combining the columns in the data frame for title as well as artist name into one column called song. So as it will be more intuitive when we check our recommendations that the song title and the artist name would be in one column. So we see the most important columns in here with us, our user ID, represented by this user ID column, and another column called song column, which I just created here. So what a recommender system will be looking at here is mappings between the user ID column and the song column, which I just created, right? So essentially, the recommendation system, what it does is it just looks at the mappings, right? Okay, so what this cell is doing is over here, are we good till this cell? Okay, so what we'll do here is that we will see the popular songs. Based upon the listen count, what I did here is I simply sorted all the songs based upon their listen count. So we get that the Seher Kosmish by Harmonica. So you see in the song column which we just created, we get the song name as well as the artist name together. So these are my sorted list of songs, popular songs. So any questions so far? Okay. Okay, so now next we count the number of users here, unique users. So we have 365 unique users in our data so far. And then we count the unique number of songs in the data set. We have about 5,000 songs in the data set. So as we were just discussing, that this suggests to us is that the number of users is greater than the number of songs. So this suggests that there are some songs which are being repeated, which are common in between users' listen history, right? So this means that it is possible to calculate similarity between users based upon the common songs that they are listening to. And this was our criteria. Remember when we talked about building an item similarity based co-occurrence matrix, then it will be easy to build so we will be able to build similarity matrix, co-occurrence similarity matrix wherein we will have all the songs on the rows and then similarly all the songs on the columns as well, and our values for the co-occurrence matrix would be number of users who have listened to both song I as well as song J. Remember? So this suggests us that it is possible to build a co-occurrence matrix.
So you know that there's no overlap? How do you know that 65 users and 5,000 implies overlap?
Okay. So if there would be no overlap if there were 365 users and 365 songs. Maybe not. So means that we can map one user exactly to one song. Right? If there were 365 users on my left and 365 songs on my left, maybe we can do a one-on-one mapping. Right? But now we have only 365 users on my left and about 5,000 songs on my right. So if we are mapping one song to one user to one song, we draw a line like this. So when we are finished with all the 365 users, we would have used just 365 songs from our right-hand side list, right? And we will still have 5,000 minus 365 songs still left, which have been listened by some users, right? So this can only happen if one user is listening to more than one song. I mean, it is possible that all those remaining songs were listened by only one user and there is no overlap. So actually, it is possible that there is no overlap between the songs user are listening, but it is very highly likely I would say. I won't say that it is for sure, because it is possible that all the remaining 5,000 minus 365 songs were listened by just one user. It is possible, yes, that there is no overlap. Yeah, you're right. But this suggests that it is very likely that there is an overlap. And since I have already seen the data set, I know that there is an overlap. So we'll see now how it works. Okay. So we'll create a song recommender now. For that, we will split our data into training set and test set. And usually, we'll follow the usual rules of creating training and test data, wherein we will have 80% of the data as training data and 20% as test data. So what we will do is that we will build all our recommender systems on our training data, and then we will evaluate them using our test data using precision and recall curves. So the same model built on training data will be used in the test data users to get our evaluation. So our training data, just to give an idea, looks like this, just ahead of the training data. And so let's build a very the simple popularity-based recommender. And so we'll create an instance of the popularity recommender class. So this popularity underscore recommender underscore py, it is a class in the recommenders.py file that is in GitHub. So this step is simply creating an instance of that class. Right? We are good till here? Okay? Yeah. So next what we do is we will use the popularity model to make some predictions. And we see that these are my top songs over here for users of 5. The Seher Kosmish by Harmonica, then Undo Bjork by Bjork, Dog Days Are Over by Florence, then You Are the One by Dwight Yoakam, and similarly all these other songs. Then let's take another user now, which is users of 7 in this case, and make recommendations using the same popularity-based recommender over here. And what do we see here? What are my recommendations here? They are the same as the previous case, right? So this suggests that there is no personalization in a popularity-based recommender system. So no matter what the user is, you could change it to any other user, and we will still see that the same recommendations are being recommended. Right? So are we good till here? Right? Okay, great. So now next we will build a song recommender using personalization. What we talked about, item similarity-based personalized recommender system. So as I was just talking, our co-occurrence matrix here would be a song-by-song matrix, wherein each cell would be a normalized value of listen count. Right? So let's create an instance of this class. And then again, we will recommend for the same users of 5, which was used in popularity-based recommender case. Let's make some recommendations. Okay, so it's doing the calculation here. So, okay, the results are here. So, so in these results, we see that it says training data songs for this user ID. So users of 5, which is the user in question, this is the ID for that user. And we can see in the training data that these are the songs which this user has been listening to so far. And we have to make recommendations, more recommendations for this user. So we see that there are some songs by Eminem, some songs by Lady Gaga, Salt and Pepper, and Destiny's Child, and so on, right? And we see what are my recommendations here. Okay, so we can see some songs, more songs by Eminem, some by Justin Bieber, and and then also we can see that these are my score also here. And one thing I would like to point out, remember when we were considering the case of, in the slides, Bob, when we had to make recommendations for Bob, so we had, when Bob was watching just single movie, then we took the row A for Bob and made the recommendations. Now think that this users of 5 is Bob here, and he has watched all these movies over here. How many movies are these? 13 unique songs for this user already. So how many rows of co-occurrence matrix will we take in this case? 13 rows, right? So we will take the 13 rows from the co-occurrence matrix corresponding for these 13 songs, and we will calculate, we will get the co-occurrence matrix value of all these songs with all other possible unique songs, which in our case is 5,000, right? So we will construct, so our matrix here would be, that we are considering here is 13 cross 5,000, right? And we are calculated, so we will normalize, we will just calculate a weighted sum of all the columns in this 13 cross 5,000 matrix to get our weighted sum. And then whatever weighted sum we will get, we will calculate, we will rank them to get these final recommendations. That makes sense, how we are mapping the toy problem we discussed earlier to a real-world data set? It makes sense? Okay, great. And those weighted scores that I just talked about, these are those weighted values which have been sorted now to give the rank of recommendations. Okay? So how about now you try to calculate personalized recommendation for this users of 7. So we can make use of the previous code. How about I copy the same code from here, and I fill in here. Okay, just run it. Okay, so it's still calculating, but before that we can see that this is my user ID. So in this case, this is my Bob over here, the ID for Bob based upon what we learned in the slides. And these 8 songs are the songs which Bob has already listened to. So what would be my co-occurrence matrix in this case? 8 cross 5,000, right? So these 8 songs, we will take the rows for these 8 songs in the co-occurrence matrix, and we will calculate a weighted sum of these normalized values, right? And then this weighted sum, we will rank it, we will sort it to give the final scores over here. So looks like this, in this case, Bob only likes Coldplay songs, no other song. And let's see what our recommendations are in this case. So some songs from Coldplay and maybe some other songs by some other singers as well. I don't know much about other singers, but I can't say if they are relevant or not. But our data was very small, so when we do it, I was also running it over a larger subset of data at home, and I saw that there were further more Coldplay songs being recommended on the larger subset of the data. But here, since our data is small, we see some other songs as well. So does this make sense? Right? Okay, so next we move on to another usage of the same model, item similarity based model. In this case, we are going to use our model to get similar songs to any given song. So let's say we get similar songs to this song You Smile by Justin Bieber. Okay. Okay. It seems like there are quite a few songs by Justin Bieber which are coming in as similar songs to this song, and then some other songs as well. Okay, so how about a quiz for you to calculate similar songs for this song Yellow by Coldplay? So what we can do is we can again copy the same code from here, from our previous case, and let's see, we can paste it here. Instead of this You Smile song, now we have this Coldplay song, and let's run it. Okay. Yeah, so these are the similar songs to this song. So in a way, these are the nearest neighbors of this Coldplay song based upon similarity in purchase history. So what we are doing here when we are in the model, what it is, the code, what it is doing is that it is picking the row for this song, Yellow by Coldplay, in the co-occurrence matrix. And so in this case, we are taking 1 cross 5,000. So for this song, we are getting the co-occurrence matrix values for just one row corresponding to Yellow Coldplay song. And then these normalized values, we are simply sorting them, and then the sorted list by score is being listed over here as our final rank list. Right? Okay. Right. So next move on to comparison, quantitative comparison between the models. So we will compare the two models which we just built, popularity based and the item similarity based model. So we can run this step. I think it will take almost a minute to do this calculation. Right, this step. So what this step is doing is, over here, it is making records. So what, in order to calculate precision and recall, what exactly we have to do here is that, so our models, both popularity models and the item similarity models, were created using the training set. Now we also left out some data in the test set earlier. Remember, 20% of the data is test set. So what I did was that from the test set, I took out users, which using a user sample, in this case, which is 0.05. 0.05. Okay. Actually, we can increase the user sample to 0.05 here, but that's okay. So the idea is to get some test users which are also there in my training set. Right? So why do I want this? because my recommender systems model was built on training set. And in order to evaluate it, I need some users which are also there in the training set as well as in the test set. So these users we'll be able to compare that this user listened to some songs in the training set. So the recommendations made, if we keep in mind our image that from the slide where I had some Will Smith movies and the Johnny Depp movies. So let's say all the relevant songs for the users are the songs which are there in the test set, the known songs which I know that the user likes, and all the recommendations which I had in that slide on the horizontal axis. Those are the recommendations from my training set. Right? Is this clear? This mapping that what is the basis of calculating precision and recall here? So I'll repeat that all my relevant items are the ones from the test set. I'm assuming that. And all the recommendations are the ones which are in the training set, which are generated by the model which was built on my training set. Okay. So I will change this value to 0.05 just to have a bigger sample. And run this again. Because 0.05 sample was just having one user in it. So we need a little more bigger user sample. And so what it is doing is it is calculating recommendations both using popularity model as well as the item similarity model. And for each step, it is calculating precision and recall values. And then in the next step, when the precision and recall are all calculated for all the users in my user sample, we will calculate the precision recall curve in this step. So we are just waiting for this step to finish over here. Are we doing good so far? Good, great. Okay, so it's done now. All right. So this code, now next cell we will run, which simply plots the precision recall curve. And then this will plot. Okay. So this is what we get here. So so this is a very small subset of the data. That's why the precision recall curves will not be like what were there in the slides. But just to get an intuition, so this blue curve here is the popularity model, and the green curve here is the item similarity based model. And we can see that the precision recall values are higher even in this subset for item similarity based model. And I want to make a note that whatever curves you will be getting on this data set would be different, because the user sample, what the code is generating is random. So the shape of the curves you will be getting here would be different. But what I also did is that I also ran the whole model at home on a larger data set in order to get precision recall curves on a bigger data set, so as to give you an idea of how it will look like on a larger subset of data. So what I did is I ran the code on that subset at home, and then I pickled the results. So meaning that I persisted the results. In Python, we do that using a library called pickle. And here, I'm simply reading those pickle results, and I will just shortly show you how the results will look like on a larger set. But before that, I want to point out that for persisting the results, I saw that for Python 3 and Python 2.7, it was supporting different formats. Therefore, I persisted the results once using Python 3 and then once using Python 2.7. So those of you who have Python 3, I would suggest you run this first cell over here. And those of you who have Python 2.7, I would suggest you run the second cell. So I have Python 3 on my laptop. So I will run here. So this is what I get. So on a larger data set, you see the green curve shows the curve for item similarity based model, and the blue curve shows the curve for popularity based model. So you see the area under the curve for the precision recall curve for the item similarity model is larger, and so we can say that this curve suggests that the item similarity model, which was a more personalized model, is giving better recommendations than a simple popularity based model. So were you able to run this step? Okay, great. Okay. So if we are clear till this step, I want to move on to matrix factorization based system, recommender system. Okay? Right. So for this matrix factorization based recommender system, I wanted to give just a brief demo of it, that how the matrix factorization is working behind the scenes. I don't want to use it on a real data set where we don't understand at all that how it is working. For that reason, I simply chose a very small matrix so that we understand the behind the scenes work of this method. So this is the matrix what I chose. I simply created this matrix which has users on the as my rows and items as my columns, and these values here are my ratings. So it is a simple matrix, and then the code that follows will be implementing SVD. So this code I want to mention is that this is an adaptation of a code from this GitHub source. So what we will just run it now. So I want to point out that you can see here that in Python there is a support for matrix factorization using this library sparse SVD, which we are importing. And then Python also supports sparse matrices using this library CSC matrix, which we will be using. And then there is this SciPy library, which not only supports sparse matrices, but it also supports linear algebra-based calculations in this library, linalg, and we will be using this for matrix factorization. So we'll just run it. Okay, and then we run this step as well, which has the methods to compute SVD as well as the final recommendations. Okay. So now what we will do is we will calculate our recommendations. We will use the methods which have been just built in order to make recommendations for a test user. So this is my matrix. Remember the matrix which I had just talked about over here? This matrix, how will we represent this matrix in Python? Anybody knows? Using a NumPy array, right? The Python has a support for matrices. So we'll create a NumPy array for this matrix, and the last we can see that I created this user ratings matrix as that the first 0, 1, 2, 3 users, they have all the ratings with them, but the last user, which is user number 4, has rated only one movie. And our task is to generate recommendations for this last user, right? So what I did was I created a test set in which I simply put just user number 4. And then I call this, the methods which we wrote above to compute estimated ratings for this user. Let's see what we get. So we get here for user 4, 2. These are my predicted movies actually. So first movie number 2 is being predicted, and actually one thing I want to mention here is that I purposefully left the movies here in the recommendations which the user has already seen. So you see the test user over here has already seen user number 2, has only seen movie number 2. But so it is being, over here, this is the topmost movie being recommended, and I purposefully left it to get an intuition. So So my top recommendation here is 2, movie 2, then movie 1. So we can go back in this matrix and check out. This is my user 4. So this item he has already watched, and then item number 1 is the second item that is being recommended here, and I wanted to just show you a demo that if we change this the movies which the last user has already watched, then the recommendations will change. So previously our recommendations were movie 2, 1, 0, and 3, and now they have changed now, right? And so based upon so the weighted sum that is being calculated will be different here. And so the recommendations change. So what I wanted to show here next is that, so this quiz we already did just now that we changed. Okay, let's change it to this value. So now we'll simply change it to some other value and see how the recommendations change. Okay. Yeah. So for this quiz, we see that when our test user has rated only movie 0, then we get these recommendations over here. Okay. So now the most important part now comes to understand the intuition behind SVD here. That so given our user items matrix, how is the SVD acting on that matrix? So remember we talked about that SVD result gives 3 matrices as outputs, U, S, and V transpose, where T here means transpose. So we talked about how matrix SVD will transform that initial given user ratings matrix to vectors in the latent dimensional space. So I created a sample code so as to that how those vectors will look like in a 2-dimensional space. So in SVD, US, for the S represents how many latent dimensions we will have here. So in this case, in the code here, I kept the value of K here as 2, which means the number of latent factors, so as to give a demo of user and item vectors in a 2-dimensional space. So this K means a number of 2 latent factors. So remember, in the figure that I had in slides, we had two-dimensional figure, and they represented how much of a serious movie the user likes and how much of we were quantifying that how much the movie is serious versus non-serious, and how much the movie is geared towards males versus females. And similar for users, we were quantifying a value to each user that how much this user likes serious movies versus escapist movies. So just now we map the same slide over to this scenario wherein we have this small matrix and we are representing users and items both in my latent dimensional space, wherein it is a 2-dimensional latent space. So this code here will do that. In the end, I'm using PyLab in MATLAB to make this visualization. So this is what we get. So this is my latent dimensional space for this problem, which is a 2-dimensional space. And these stars represent all my users. And all these items are represented by these tiles. So you see that in that slide, I had these nice captions that my latent dimensional space is represented by these genres, serious, escapist, movie geared towards males or females. But when we are actually doing this matrix calculation, SVD in the code, it doesn't tell me automatically that what are my dimensions called. In reality, when we do the matrix factorization, the dimensions would be very abstract. And this is just 2-dimension. And when we take in more genres, let's say more dimensions into account, like For example, in case of movie genre, serious, horror, comedy, and so on, we will have a multi-dimensional space in which users and items will be represented. And we have to understand this dimensional space so as to come up with, so as to make a mapping between these abstract dimensions into some specific genres. So this mapping has to be done by understanding this data somehow. And so the point I wanted to make clear is that these latent spaces are very abstract when you do the actual matrix factorization in the real world. But just to give an idea that how these users and items will look like in the latent dimensional space. So when a new user will come, we will, again, given its ratings, we will plot it out in the latent dimensional space that where this user lies, suppose here. And then we will find out what are the users and items in the vicinity of that user in that multi-dimensional latent space, and we will use them to make recommendations. Right? This makes sense? Great. Okay, so this finishes the notebook, and I will go back to my slides here. Okay, so these are some of the resources I would like to recommend you if you want to study further about recommendation systems. Yeah, so I'm also making a recommendation to you today that I followed this book, Recommendation Systems: An Introduction by Dieter Janak, and then this book, Massive Mining Datasets by Yor Leskovec, it builds background first about matrix factorization methods and other mathematics-based concepts, and then it goes to, it has a chapter on recommender systems. So if you want to read all the background also, then this second book is quite useful. And then there is a Coursera course on recommender systems by University of Washington. In fact, I followed this course quite a lot. I had, there is a previous course which builds onto this recommender systems, and I just finished that course, and the material gained some inspiration from that course as well, what I just used. And then there is another course on Coursera by University of Minnesota on recommender systems, and if you want to go further into details. And lastly, I thank you all for joining me here today for this tutorial. I hope that you enjoyed this tutorial, and if you have any questions, please ask me now.